All right, this is going to be a redo of the lecture that I gave on the 22nd of November that I called 22-11-16. Okay, that was, you might realize that was quite garbled. Some of the sound was quite removed from the actual video. So I'm just going to check the sound here. Yep, sound works. And so we're in business here in terms of being able to have the lecture recorded on YouTube. Great. All right, so now in that lecture, I started with reviewing a little bit of, well, I didn't review it very much, but the previous lecture I had looked at power functions. Okay, so these are functions of the form a to the n, ax to the n. All right, so then I think I also looked at the endpoint behavior of these functions and especially what their behavior looks like at the origin. Okay, so in this section, this is what this section, the section that I intended to cover in this lecture was 5.3. This starts to deal now with polynomial functions. All right, so polynomial functions are functions of the form, in general, where you have a leading term times an times x to the power n. Okay, so this is just the name of the coefficient. A sub n is just the name of the coefficient. And an has to be non-zero. So for some n. And then lower order terms. So these might be 0. And they go all the way down to, right, so this is a coefficient times x to the power n minus 2. And the last few terms will be a2 x squared plus a1 x plus a0. So that's a general polynomial function. Okay, in some specific cases where I did it kind of in reverse order, but I should do it in increasing order of difficulty. So one case is where where n is 0. And then f of x is just the last term, or the last constant. So that's just the constant function. Okay, so now for each of these I'm going to give the degree. So the degree is the leading is the power of the leading coefficient. So in this case, the leading coefficient goes all the way. That's going to be the leading coefficient. All of these are 0. And so you'll get degree is 0. Now the only exception to that would be the 0 case. So this is the case if I take a0 to be non-zero. But if I take a to be 0, then I'll call this degree minus infinity. It's just a convention which is helpful for when you deal with multiplication of polynomials or addition of polynomials. If you add polynomials, the resulting degree is always the maximum degree of the starting polynomials, and if you multiply polynomials, the final degree is always the sum of degrees of the starting polynomials. But if you multiply by the 0 function, then you should get 0. You of course get 0, and so the degree should stay the same, namely minus infinity. You don't add 0 to whatever you had before. Should make it all as small as possible. So minus infinity added to any positive number gives you minus infinity. Okay, so that's why I have this exceptional case. So really, when we talk about polynomials with a degree, with a normal positive or 0 degree, we're talking about non-zero polynomials. Okay, so n equals 1. That case would give you f of x is equal to a1x plus a0. So that's the linear. That's a linear function. Here, a1 is not equal to 0. Yeah, actually, in this case, if the leading term is, if I were to make this requirement, then automatically, in this case, the leading term is already non-zero. 0 is excluded. So I include this as a special exceptional case. So that's really what I should have started with, I guess. So here, for a linear function, you have a1 not equal to 0. And this is, yeah, this is a case we've dealt with before. So linear functions. The graphs of these are straight lines. The graph of this is a straight line, but it's always a horizontal straight line. But this might have a slope and a y-intercept. It always has a y-intercept, but anyway, the slope here is always a finite slope. That is, it's not infinity. Okay, so those cases we've seen before. And then this case is the quadratic case, n equals 2. Oh, the degree of this is 1. Is there a degree column? And the degree of this will be 2. a2x squared plus a1x plus a0. That's a quadratic function. Okay. And so on. For the general degree, for the general function, then the polynomial is of degree n. Okay. And the degree n equals 3 case is called a cubic. So it starts with the non-zero. This is non-zero. A non-zero x cubed term, and all the rest. You have 3 other terms there as well, quadratic terms. Okay. Now, in picturing these graphs, okay, remember we could picture these first two as straight lines, and this will be pictured as a parabola. The graph of a quadratic function in general will be a parabola, either opening up if a2 is positive, or opening down if a2 is negative. For higher cubic equations, it becomes more complicated. Okay, so it turns out there's sort of a typical shape of the cubic graphs. They might go up smoothly without going down, so no turning points. We'll see that what turning points are later. So it might go up like this, or it might go down and then up, or it might be this critical case where it goes to a slope of 0 and then goes up again. So it goes horizontal briefly or instantaneously, and then it goes up again. So there are these 3 cases for the cubic. Okay, so the question is, how do you graph these polynomials for the higher n case, higher than n equals 2? Okay, so I'll deal with ways we can do that in this lecture. So one way is to look for the roots of the polynomial. Okay. So the roots are also called zeros. So in order to graph polynomials of degree n greater than or equal to 3, one thing we can do is look for the roots, or also called zeros, or also called x-intercepts. Of the polynomial. Okay. And we'll see later that when you look for roots or zeros of a polynomial, you might have real roots or complex roots. If we just deal with real roots, then there's no difference between real roots or zeros and the x-intercepts. They're the same. But if you have complex roots or zeros, those are values of x which are complex values, which when you plug it into the function gives you 0. They have no x-intercepts on the real x-axis. Okay, so in that case, these terms will be different. Okay, so in this section, we'll usually consider polynomials where the roots are all real. And so the x-intercepts will be all real as well, and you can see them on the graphs in the xy plane. Okay, so let's see how this is done. So I look for the roots of the polynomial. In order to do this, it's really helpful to factor the polynomial, or find the factored form of the polynomial. So I'll start with either this factored form is given to us, or that it's not too hard to find, and we can just do it by just trying trial and error. Okay. So one example would be this function f of x is equal to x cubed minus 2x squared plus x. Okay? All right. So remember how to factor things. Usually we will look for a common factor to all the terms and then bring it out. So that's one way of bringing it into completely factored form. So we'll do that here, and we take out a factor of x, and we have x squared minus 2x plus 1. And then if you have a quadratic, you look for ways in which you can factor this quadratic factor. So in other words, this is called a trinomial, because it has 3 terms. So trinomial factorization, okay, it can always, you should know how to do that. It can always be done by finding, for example, finding the roots of the quadratic function here, and you can use a quadratic formula, and then you can write the whole thing as a difference of the product of the x minus one root and x minus the other root. Okay, another way to do it is complete the square. So you can always factor this by completing the square, and then factoring something which will be the difference of squares in that case. Okay, in this case, it's easy enough. It turns out to be a perfect square, and so it's just x times x minus 1 squared. All right, so that's just by guessing. You can guess the only factors here are 1 and 1, or minus 1, and you pick whatever sign that gives you minus 2 here. All right. Now that we have the factored form of the polynomial, what does this say about the graph of the polynomial? Okay, so if we plot y is equal to f of x is equal to x times x minus 1 squared, what does that look like? Okay, so here's the xy plane, x-axis and y-axis, and we're told that so you can read off where the zeros are just directly from this factored form. So there's zeros at, or x-intercepts at wherever y is equal to 0, right? So wherever y is equal to 0. So you set this left-hand side equal to 0, and then either x equals 0 or x minus 1 squared is equal to 0. So x equals 0 or x equals 1. Okay, so on this axis here, and then at 1, just here, let's say, you have, the graph will go through that point. So the points that it goes through are 0, and when you plug in, yeah, y is 0 in both cases, right? So these are the intercepts. Okay, so here and here, these are points on the graph. Now the question is, how do you draw the graph nearby? All right. Okay, so in order to draw the graph nearby these points, I'm using some notions from, well, I'm kind of using notions from calculus, but I'm trying to make it easy here. You don't have to know calculus to do this, okay? What I'm doing is I'm near the point x equals 0. Okay, so near this point here, what is the factor that mostly contributes to the value of the product of these two factors? Okay, it's this factor here, because if I make this factor small, as small as I like towards 0, then this whole thing will make the whole thing 0. Whereas if I take this to go to 0, it'll just give me something near minus 1 squared, which is 1. Okay, so if I adjust x a little bit, this factor will give me the greatest overall effect. Whereas if I adjust this factor a little bit, it doesn't really change the overall expression very much. Okay, so this works especially if I have a single root factor like this. So here's this means that there's a root of multiplicity 1 at x equals 0. Okay, this has multiplicity 1, and this has multiplicity 2. Okay. Now when all the roots are real, then I'll be able to factor this completely in terms of polynomials which are linear and where you're subtracting a real root. You're adding or subtracting a real constant here in these factors here. So I can always factor this over the real numbers, and in terms of linear factors. Okay. So if all the roots are real, as opposed to complex, then can always factor into these linear factors. Okay. And each factor might have powers associated with it, like this one does. So if it has a power, then that means that root whatever that root is that makes this 0, is repeated. And I call that that repeated root something with multiplicity 2 or 3 or whatever. If it's just a linear factor by itself and there are no others like it, then that's multiplicity 1. And now it turns out that if I include all the multiplicities of all the factors, it will always have to be the same as the degree of the polynomial. So the sum of the multiplicities of all the roots is equal to n, the degree of the polynomial, which in this case is 3. So you can see 1 plus 2 is indeed equal to 3 here. Okay, so near the point x equals 0, the behavior of the polynomial will be determined mostly by this form, and this will act roughly like a constant. So this is helpful for seeing whether that's a linear part, whether that's a line going up or whether it's a line going down, because you can simply evaluate this other factor at x equals 0 and get the coefficient of the linear function, the coefficient. So that's the slope, right? So let's write that out then. So really, the book doesn't go into this much detail as to finding the slope for linear factors, but this is a rule for a linear factor. In a fully factored polynomial. Polynomial. Find, so it'll look like this, x minus r, and then all these other factors here. Okay, so let's see what I mean by that. So let's say we can write all the factors in this form. So this is a fully factored form. So each S1, so these are the roots. Okay, and the multiplicities, M1, are the corresponding multiplicities for each root. Okay, so clearly, if so, M1, call them Mi, they have to be bigger than or equal to 1. If you have a root at all, it's either going to have multiplicity 1 or it's going to have multiplicity bigger than 1. And the sum of all the multiplicities must be n. So the sum of all the multiplicities from I going to 1 to L, from 1 to L, is n. And so L must necessarily be less than or equal to n here. Okay? L can be equal to n only when all the multiplicities are 1. Okay, so now if you have, let's say, M1 is equal to 1, then you have x minus S1 by itself, and then you have a whole bunch of other factors like this. You have all the other factors. So let's say the M2, ML, they can be 1 or 2 or bigger. All right? So in order to find the behavior through this root, it'll be a linear function because all these other roots are different. So if you take x equal to s1, you'll get something close to 0, and that'll make the whole thing 0. But if you take x close to s1 in each of these factors, this is going to give you something non-zero. So these are, in other words, these are distinct roots. Okay, so if I plug in s1, s1 will make none of these factors vanish. Okay? That distinct means they're all completely different from each other. All right, so, but that will give me some non-zero quantity, and then that will actually be like the slope of this straight line. So evaluate at x equals s1. You get something not equal to 0. Okay, call it A or something. So then the function, this is my factored polynomial, then my polynomial is approximately equal to this constant, whatever I evaluated here, times this part, near x equals s1. All right? So A will be the slope of the straight line that passes through that. So in some sense, I'm finding the slope of the polynomial right at this root, right at the x-intercept here. Okay, so that's a rule for, it's to determine not only where the function passes through the x-axis, but how it passes through the x-axis if you have a linear factor. Okay. So for example, back to our example, near x equals 0, you plug in x equals 0 here, f of x behaves like, you just evaluate this at x equals 0 and you get -1, and then you square the whole thing and you get +1. So my capital A is just 1. So the function acts like a times x near x equals 0, which is just x. Okay, so back to our function here. Let's draw the graph back in. It looks like the straight line x. So here, if this is 1 and this is 1, then my graph looks like this. Something like this. Okay, that's the line y equals x. Now over here, which is at x, near x equals +1, near x equals +1, the graph looks like close to 1. It looks like just this quadratic term, because if I change x minus 1 is close to 0. If I change that slightly, I'll get a drastic change in the whole function. Whereas if I change from, let's say, 1 to 1.01 for this factor, it hardly changes anything at all. So again, there's a rule. It's kind of a rule now for any factor. So you can just isolate that factor, and then evaluate everything else around it. So all the rest of the factors, where you plug in the root into the other factors, you'll get something non-zero, because all the other factors have distinct roots in them. Okay, so near x equals 1, x is approximately, this is approximately 1. And then the rest I'll keep. So this is approximately x minus 1 squared, which is a parabola. That's a parabola. And it's opening upwards, because this factor is just 1 in front. So it's a parabola opening upwards. So it looks like this. The vertex is at x equals 1 and y equals 0. Right? So So it's a parabola with a vertex at 1, 0. Okay, so that looks like this. Actually, it looks more like it's spread out a little bit more. So it'll go actually through this point here. But it's nearby x equals 1 that I want to draw the graph carefully and as a solid line. The rest is just, okay, the approximation no longer holds very well over here for the whole polynomial. So the graph looks like it's going up through the origin like this at x equals 0 with slope 1, and it goes into this parabola which is this thing over here near x equals plus 1. In between, you connect it. It has to be done smoothly. Okay, so polynomials have no abrupt changes. So these are general features. So they're smooth, so you can draw them always in a curved way without corners. And also the range, or the domain, is all the reals for all the polynomials, because they're well-defined operations for any real number. Okay, so the domain is always all real numbers, so there's no places where you have missing points because it goes off to infinity or something. Okay, so it'll actually come up from here, it'll curve around like this, and then go up like this, something. Okay, so that's going to be what the graph of this polynomial looks like. So you can determine that graph mostly from this factored form. It shows you the behavior near the roots. Furthermore, you can find the behavior at large values by considering the leading order term of the polynomial. So what's the leading order term of this polynomial? Well, if you expand it out, you would get the full factored form as we started with, x, or the unfactored form, x cubed minus 2x squared plus x. The leading order term is the largest degree term, where x has the largest power, and that's x cubed. Okay, so the leading behavior of the polynomial is determined by this factor, because as x gets larger and larger, either plus infinity or minus infinity, this term will dominate all the rest. This term will eventually get bigger and bigger than all of the other factors combined. Sorry, all of the other terms combined. Okay, so this will look like x cubed. What does x cubed look like? As x goes to plus infinity, y goes to plus infinity, because it's an odd power. As x goes to minus infinity, y goes to minus infinity. So this behavior is consistent with this power law behavior of the leading term. Okay. So first of all, the rule extends to any factor in a fully factored polynomial. So near it, so if m is bigger than or equal to 1 now, you could still evaluate this like I did here. So this would be the rule for any factor now. All right. All right. So any factor form will also have this kind of rule here. Okay, so that's how I can determine what the shape looks like. And then the behavior at the endpoints, I called it endpoint behavior. as x goes to plus or minus infinity, the behavior is determined by the leading term a n xn. Okay, the factor in front is important because if that factor is positive or negative, then that'll flip everything. If a is positive, then it will, for the cubic, it will go like this. If a were negative, then it will change the behavior so that as x goes to plus infinity, y goes to minus infinity, and as x goes to minus infinity, y goes to plus infinity. Okay, so that all the four cases where either n is odd or n even, and an is even, or sorry, positive or negative, right, there are four cases which are all enumerated in the book. It's hard to get a good horizontal line. All right. So you can also show the shape. It's sort of like this, 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 this. Okay, so that's kind of that summarizes all the four possible cases. All right. For higher, then if you have an odd n which is 5 or higher, then you'll get the same behavior, but you might have differing behavior inside. So I should probably exclude the middle part here. So you don't know what happens for higher. I'll just show the end results by the arrows here. Okay. All right. Okay, let's look at another case. Now we're going to deal with a case where you have all three factors are linear. So all multiplicities, you have three real roots. It will be a cubic equation, and all the m's will be 1. Okay, call this example 2. Sorry, I didn't label the previous example 1 before. Okay, so this one is f of x is equal to x cubed minus x. So again, I factor out the x, and I'm left with x squared minus 1. And then I can factor that because that's a difference of squares, as x plus 1, x minus 1. All right, so for each factor now is linear. The multiplicity is 1 for each factor. So I have roots of multiplicity 1 at -1, 0, and 1, just to put them in increasing order. So the multiplicities are 1, 1, and 1. So again, it adds up to 3, which is the degree of the polynomial. Also, the end behavior is of this form, because the coefficient in front of the x cubed is going to be positive. Okay, so I find my zeros. They're -1, 0, and 1. Here's the x-axis. Here's the y-axis. Okay. And now I'll use my rule for linear factors, where you evaluate the rest of the factors at where x equals that root. So let's try it for x equals 0. That's kind of the simplest case. So at x equals 0, what does the other factor look like? Well, you plug in x equals 0 here, and you get 1 times minus 1, which is minus 1. So a is equal to minus 1, and f of x is approximately equal to minus 1 times x. Okay, so I evaluate all the other factors, not the actual factor which gives you the root. So it's going down, actually. So it's a negative slope line. Here's my 1, and here's my minus 1. It's a negative slope. It has minus 1 slope here, like that. So just nearby then, that graph looks close to that straight line. All right? And let's do it for the other cases. So near x equals minus 1, I have this factor. So my function will be approximately equal to this factor times the constant that you get by plugging in x equals minus 1 into the other two factors. So here a is equal to minus 1 times minus 1, which is that's minus 2 times 1. That's the whole thing is positive 2. So that's what I put in here. Okay, so near where x equals minus 1, the graph will go through the, this, if you check this, the y-intercept is indeed, or the x-intercept is indeed minus 1. And it will come along, it'll go up with slope 2. So that's kind of going like this. All right? I'll draw the minus 1 outside so it's a little bit more clear. And over here, at x equals plus 1, again, I write the factor which gives me 0 when x equals plus 1. I leave it unchanged. It's going to be x minus 1. Yeah. And I plug in x equals 1 into the other two factors and evaluate that. And that's going to give me the coefficient in front. So this is approximately a, where a is equal to 1 times 1 plus 1, which is 2. 1 times 2 is 2. So again, it will have slope 2. It will be a line of the same slope as this one. All right. Okay, and again, the end behavior is going to be like x cubed, which goes up to infinity as x goes to infinity. Y goes to infinity as x goes to infinity. And over here, it's going to go to, y is going to go to minus infinity when x goes to minus infinity. So it's going to look like that. So so you can now join the lines as, if you like, connect the dots. So it'll look something like this. It'll come up from minus infinity like this, go through at this slope, and then go down through here, and then up through here, and then keep going. So that's roughly what it looks like, the graph of this polynomial. Okay. So these rules are intended to help you look at the behavior near the roots in order to help you draw the rest of the polynomial. But you can always check. Well, there's several ways to check this. If you have a graphing calculator, that would help you, or some other technology. Or Maple would be another technology if you have access to that. Or I think Maple TA has, in some of the problems you're able to use a graphing capability, which I'm still learning how to. I'm trying to learn how you would implement that. But in other words, you can write down the formula for the polynomial in Maple, and it will just plot out the graph right away. I've been showing you examples of that, right? Okay, so so you can check it that way, or if you just have a regular ordinary calculator, you can check individual values. You can find values away from other than the roots. It just means finding a table of values at some other points. So it'll help you get an idea of where where some special points might be. If you have a calculator, you can always get a lot of information numerically. Sometimes you can't solve for the roots by factoring; it's too hard. But you can always use a calculator to guess what the roots are and get closer and closer to your guess. Okay, so there's lots you can do with the graphing calculator. You can actually use it to estimate numerically the roots. It will do that all for you. Okay, so if you have access to a graphing calculator, that would be a great thing. I'll see if I can. We have access to graphing calculators in the class, in the physics class. So I'll see if I can make those available for you. Okay, so now find values other than the roots. Okay, so if we try x equals 2, for example, plug it in. X equals 2 is 8 minus 2, which is 6, so that's somewhere up here. That seems about right. It's already off the scale. This is only 2, so it's way up here somewhere, so that kind of makes sense. And let's try halfway between 1, 0, and 1. What is the value there? So let's try a half. And then we get x cubed is 1/8 minus 1/2, which is 1 minus 4, which is minus 3. Yeah, so it's between 0 and minus 1. So that makes sense as well. Less than minus 1/2 in absolute value. Okay, so now what else can we say about this graph? Or how can we see that? How can we check to see if our picture here is correct? Well, one way is symmetry. So it's looking like the roots are symmetrically placed about the origin. You have one here and one here. And you have similar behavior over here as you do here. So one thing to check to see is, does this have any symmetry? And actually, it does have a symmetry, namely odd symmetry. Now, how can you see that from the original equation? Okay, if the equation originally is just a sum only of odd terms, then it has an odd symmetry. Okay, so let's just go back here. So check the symmetry. So if f consists only of a sum of, so it only consists of odd terms, odd powers of x, then the whole function is odd. Because if you plug in minus x into the equation, each term will give you an extra minus sign times the original term. So the whole factor of minus 1 will come right out into the front. So the function is odd in that case. Likewise, if f consists only, if f only has even powers of x, then it's even. So if you plug in minus x then that will be the case, for example, if you have f of x is equal to x squared minus 1. This will be a parabola. It will have vertex at 0, minus 1. It'll go through the points plus 1 and minus 1. If you check the slopes, there will be about 2 in each place, so you'll get a graph that looks like this. The slopes will be, the instantaneous slopes will be actually 2 at where the graph intersects like this. That will be 2 if x equals plus 1, and the other, if you go the other way, x equals minus 1, the other factor will be minus 2 actually. So you have the odd symmetry, means that the slopes will be the opposite of each other at the symmetric points. The even symmetry, sorry. So even symmetry means this is equal to f of x without an extra minus sign. Okay. So symmetry, and if it's neither the sum of only odd powers or only even powers, then it doesn't have a symmetry like this. Okay, and you can check the graph does look a little bit, it does look symmetric, as it should. Here as well. All right. Now I think I discussed finding roots in general. So for quadratics, you can always find roots by using quadratic formula. For cubics, there is a formula but it's hard, so we'll not deal with that. So also for quartic, you can do it in principle. There's a way to get a formula. But difficult. And then for quintics and higher, there's no general formula. Okay, so this is a realm of higher algebra, abstract algebra, and so it's not we're not going to cover that. But you can always use numerical techniques. Basically, what you're guessing the roots. You guess the roots, and then you can get a lower order polynomial once you get a good approximate root, and then you can continue guessing roots for the lower order polynomials. And we'll deal with that in the section involving the factor theorem. Okay. So, but in this class, we won't have to deal with difficult roots, finding roots like that. But we'll mostly deal with roots which are rational numbers. Okay. If they're not rational numbers, then it'll be, well, obviously irrational, and they're much harder to find those, and you have to find those numerically in general. All right, so another exercise that I wanted to do is 23. This is in section 5.3. And it looks like this. F of x is equal to x to the 5th minus 5x cubed plus 4x. So you're asked to find the x-intercepts. So that's all you have to do. Okay, so first of all, looking at the leading order term before we factor, it's an odd leading order power. And so because it's odd, it will have endpoint behavior which goes up like this and down like this as x goes to plus infinity and y goes to plus infinity, and as x goes to minus infinity, y goes to minus infinity. So it'll look like that. Okay, second, we'll factor it. So factor out the x first, and you get x times x fourth minus 5x squared plus 4. Okay, so then factor this. You can keep on factoring this because you can think of the this as x, and this is x squared. So, right. So in case you have this sort of situation where you don't have x and then x squared here, but at least you have double the power here as you do here, then you can still use a substitution like this to get a factorizable expression. And then you factorize this, and you get x minus 1, x plus x minus 4. And you plug back in the x squared, and you get x squared minus 1, x squared minus 4. So this all becomes x times x squared minus 1 times x squared minus 4. And that fully factors into, these are both difference of squares, so that's x plus 1, x minus 1, x plus 2, x minus 2. All right, now you can read off all the x-intercepts, and they are 0. Remember, the y-coordinate, you have to include both x and y-coordinates to label a point, and the y-coordinate is always 0 for the x-intercepts. And you get minus 2, 0. I might as well put them in increasing order. So that's minus 2, minus 1, 0, 0, 0, 1, 0, and 2, 0. Okay. Now that's what the book asks. What I did was a little bit more, what I'd like to do is a little bit more here, and that is to show you the picture of what the graph looks like. Okay, so I believe I plotted this out and I gave it to you as a maple graph, and I sent it to you. I believe it's in Maple or Graphs, Math 110, Graph 2 or 3. It's a PDF file. And okay, so let's see what it looks like quickly before we move on. So once I have this fully factored form, each factor is a linear factor, and I can deduce the slope of that line, which the graph is close to, at each root. Just by plugging in, just using the rules that I had before. The rule for linear factors was, if I'm near x equals 0, then the function looks like x times a constant. To get that constant, I simply plug in x into each of these factors. If I do, I get let's draw a table here. So near x equals, and I'll put in the value of x, f of x is approximately looking like what? Okay, so near x equals 0, it looks like 1 times minus 1 is minus 1, and 2 times minus 2 is minus 4, so it's a total of 4 times x. So it looks like this with a slope of 4. 1, 2, 1, 2. Near x equals 1, let's say, it's going to look like x minus 1 is the factor that I keep. Everything else I evaluate at x equals 1. So what is that? That's 1 times, I can use a separate page for work here. 1 times 2 times 3 times minus 1, which is minus 6. So it's minus 6 outside. What about minus 1? Okay, so minus 6 is a sharp thing going down like this, even higher slope. So at minus 1, it'll actually be the same slope. Let's check that. How do I know that? So the factor is x plus 1. So I substitute into all the other factors minus 1. So it's minus 1 minus 2, minus plus 1, minus 3. Yeah, that's minus 6 again. So how did I know that? It's because it's a symmetry. It's a symmetry of the graph. I know it's odd. This is odd. Because all the terms in the expression are odd powers of x. And finally, at x equals 2, I get the factor x minus 2, that's minus 6 again. Okay, you get x minus 2 times, and I plug in x equals 2. So I get 2 times 3 times 1 times 4, and that all gives me 24, x minus 2. If x equals minus 2, then you'll see I get minus 2, minus 1, minus 3, and then minus 4, with the factor of x plus 2 remaining. So that's going to be 24 again. So this super high slope here now will make it look even steeper, and it's the same here. All right, so, and the behavior is going up like this here and down like this. So again, I connect the dots, connect the lines, and roughly I'll have this going up, a steep slope, so it goes up higher sort of. And this goes lower and then lower and then higher here. Okay, so that should be what the graph looks like. And if you check, and it should be symmetric. Odd, it has an odd symmetry. And I gave you a graph too, which verifies that this is about right. Okay, so that was number 23 at the end of that section. 48. Use a graph to write the formula for the polynomial function of least degree. Okay, so in this problem now, we want to go the other way. So instead of being given a function and asked to find the graph, or find the picture of it, or other features like the roots, we're given a graph, we'll be given a graph, and asked to find, or guess what the formula is for that graph, just based on what we know about, what the graph tells us is the behavior of the function. Okay, so this is number 48 at the end of that section. Okay, so we're given the graph, and it looks like this. So we have 1, 2, 3, 4, 1, 2, 3, minus 1, minus 2. Okay, so then it goes all the way down. It goes down to minus 2 here. Okay, so the graph starts on the x-axis at minus 2, and it goes up, and at minus 1 it hits plus 4, so it goes up like this. When it goes down, it goes through 3. Then it goes to 1. And when it hits 2, it's all the way down to minus 2, and then it goes up through the x-axis at 3 and keeps on going. Okay, so it looks like this. So that's the graph we're given. So we're asked to use the graph to write a formula, to write an expression for the polynomial function of least degree. All right, so how do we do that? Okay, so we know several things. This function must have, if it's, okay, it's a polynomial, it must have degree at least 3. Why? Because there are 3 real roots here. Okay, if it has degree 2 or less, it cannot have more than 2 real roots. All right, so that we know. The least degree, right away we can tell from the number of roots here, number of x-intercepts must be 3. All right, and furthermore, each root will have multiplicity 1 because it looks like a straight line as it goes through those roots. It doesn't look like a parabola, or higher order would be a cubic, for example. All right. Check the examples in the book. So in the examples in the book, they give you ones like this, and they show that near x equals -1. What does this look like? It's this is multiplicity 3, so that looks like a cubic through the point 1. So this whole thing is degree 6, and it will look like this. It will go down and it will go up through x here, and go through -1 here, and then keep on going. So this will be even power. This will be like x -1 cubed here. This will be like, so there's minus x to the origin. You can check that by plugging x equals into these other factors, and this will be like x plus 1 squared. Maybe there's a factor in front. I haven't figured out what the factor is. A and A prime or something, or B. Okay, so the book gives you an example like that. So the cubic, if you have a multiplicity 3 root, then it goes through, it passes totally through. It doesn't bounce like the quadratic does. It goes totally through, but it looks like a cubic there. It becomes horizontal when it goes through. So that's true for general multiplicities. Near that root, if it's even, it will bounce off of the x-axis. If it's odd, it will pass through, but it will have slope 0 right as it passes through the x-axis. Okay. So here, this is not, it's not becoming horizontal as it passes through. It goes right through with a certain slope. So that must be a linear. Each factor must be linear. And so what are the roots? Well, you can read them off. The roots are x equals -2, so that gives you this factor x plus 2, x equals 1, so that gives you factor x minus 1, and x equals 3, which gives you factor of x minus 3. Okay. So the roots are not, they don't determine, yeah, they determine the functional form of the polynomial. But there's an overall factor which we don't know, a. And now the book says you can always determine a by finding another point on the graph. So a single point should determine a. All right. Now what's a good point to choose? Well, one point, I didn't mention this before, but just as you have x-intercepts, you always have a y-intercept. The y-intercept will always be, there'll just be one y-intercept for every polynomial. Why? Because it's a function, so if you plug in x equals 0, you only get one value. So this value here will be, if I plug in x equals 0, I just get minus 3 times minus 1 is plus 3 times 2 is 6. Okay, this is the y-intercept. Right, there's always one, always just one. There's just one y-intercept for every polynomial graph, because it's a function. Okay, each value of x gives you exactly one value of y. So we plugged in x equals 0, so we only get one value of y. Okay, so, but the graph says 3. Okay, so this, I should put an a in front. So all these factors give you 6, and then you get an a. So that equals 3, so therefore a must be 2, or 1 over 2. Okay, so now if this graph is consistent, then I should be able to check it with other points. So let's just check a few other points, just to make sure. So let's draw a table, indeed, in fact. So it's, because it turns out it'll work for all the other points that are clear here. So, while checking all the roots, obviously all these factors will vanish, so we don't have to do that. X equals minus 1. So what do we get there? So if x equals minus 1, then this is plus 1, this is minus 2, this is minus 4. You divide this by 2 because of the factor 1/2, and you get plus 4. Right? And that's correct. If we check at x equals plus 2, then we get 2 plus 2 is 4, minus 2 minus 1 is 1, minus 2 minus 3 is minus 1. So that gives us factor minus, that gives us minus 2. And that's indeed what we get. So both of these checks work for the points given and shown on the graph. Okay, so that confirms that our factor, that this is a correct answer for the formula, which we were asked to find. Okay. Also, it should be a positive factor, and it is because the endpoint behavior is given by a cubic times a positive factor. It's the same. The leading term should have a positive factor in order to give this end behavior. Okay. Does it have symmetry? No. It's neither even nor odd, and that's also verified by the original formula. It has both even terms and odd terms in it. If you multiply it out, you'll see that. Okay. Yeah, I mean, if you multiply it out, let's see what you get. It's 1/2. Multiply the first two out. X squared plus x minus 2 times x minus 3. And then keep on multiplying it out, and you get x cubed minus 3x squared plus x squared minus 2x squared. So already you can stop because you have two terms which are both even and odd. Anyway, minus 3 minus 2 is minus 5x, then plus 6. And so you can see, yeah, it's neither even nor odd. It has both kinds of terms in it when you expand it. Okay, so now let's look at problems, word problems. Number 75. Okay, so here you have, okay, it's coming up to about a, I'm going to have to quit, this is almost an hour and a half. Okay, so number 75, it gives you a box, and the box is constructed from a rectangular piece of cardboard. The original piece of cardboard is 10, some unit, maybe centimeters or feet or whatever, 10 by 8. Okay? And what you do to make this box is you cut out from each corner you cut out a square of size x. So now so these are cut out and removed. And then to make the box, it will be an open box. You fold on the dotted lines. So this will be a flap which folds up, this will be a flap which folds up. All these flaps fold upwards, and then you can connect these sides and make a box. So the box looks something like this. This becomes the base of the box. So what are the dimensions of this box? You want to find the volume of this box. All right, well, obviously the side heights are all the same, namely x. Okay, so you join this side with this side. You can see it's coming up. All the heights will be x. So that's the height of the box. And then this side length here, this will be the narrow side of the base, which is 8 minus 2x. So that will be the width of the box. Finally, the longest side here will be this length of the base. Okay, so that will be 10 minus 2x. So I call it h. We call it h, w, and that's the length. Length, width, and height h. All right, so to get the volume of this open box, you simply multiply each dimension together. So length times width times height, and so you end up getting x times 8 minus 2x times 10 minus 2x. All right, so the volume is a function of x only, and it has three linear factors. So this, if you write it out, you can write it out in a factored form or in expanded form. So in fully factored form, it will be volume, let's call it v as a function of x. It's going to be, you can take the minus 2 out of each factor there, each linear factor, and so you get minus 2 times x minus 4 minus 2 times x minus 5, and then times an x, the initial factor here. So minus 2 times minus 2 times 4, it's 4 times x minus 4, x minus 5. So that's a fully factored form. Or the expanded form, for x times, you multiply this out and you get x squared minus 9x plus 20. So when you expand everything out, remove all the brackets, you get 4x cubed minus 36x squared plus 80x. So that's a fully expanded form. Okay. So I think that's all it asks you to do for now. If you want to find, let's say you're interested in trying to find the maximum volume that you can get from this box. Well, in order to consider what kind of physical situations you can get, you need to consider the values of x for which this function gives you, a positive volume. So now we're talking about the domain of x of the function. So what values of x can I have? So x obviously should be a positive number. And what's the maximum I can get? So a positive x will actually make, if it's near 0, this will be a -4, this will be a -5, and I'll get a positive value. So I will get a positive value near 0. It just corresponds to having small edges, so it'll be a very shallow box, but it will have a positive volume. As x gets bigger and bigger, what happens is that this will change sign first, and the others won't change sign. So you got a negative value if you go past x equals 4. All right. So when x equals 4, you'll get this x will have a limiting case. You'll basically subtract 2 corners, which will take off basically everything off of this side except for a little sliver here. And this part, again, everything on the other side will be taken out except for these slivers. So these are all gone. So now when I fold it into a box, it's going to be, there's one dotted line here to fold on, and I get an infinitely thin box now. So this factor will go to 0. So I'll get 0 volume there. All right, so it doesn't make sense to go past that because I'll have negative width or negative height or something. So these should be the boundaries, or the domain, the restricted values of x. Okay, I think that's all for now, and I'll see if I can include, if I need to include any other things, then I'll do that in a further lecture. So thanks for watching this video, and have a good day. Hudofis, and thanks for watching. Tashakut.